So I'll try to make this my final video then on this tidal locking. Okay, of course, tidal locking is the process here that can take a moon and make its orbital time exactly equal to its rotation time, and that's what explains why we always see the same side of the moon. So in the simplest case here, we can start with a planet that's, say, perfectly round, and let's say for simplicity it's made out of two really big chunks of rock. If that planet's going to get warped like this, then what's going to happen, and what has to happen, is that this top rock here is going to have to do some sliding relative to that bottom rock. This is going to happen in order to warp the rock, really on that internal scale like that. And of course, as I tried to tell you then, as that happens, then this energy is going to be released. This is lost energy due to friction lost energy due to frictional heating. So as I mentioned also, if you start talking about energy now, as long as we're talking about this heat energy lost due to friction here, there's kinetic energy associated with the orbit and kinetic energy associated with the rotation. That's the energy of motion. So this rock dragging business here isn't going to affect the orbit. So in other words, if a planet starts to warp like this, it's still going to continue in its large orbit around its planet. The rock dragging isn't going to hurt that very much, if at all. But then the rotation, that likely will be affected, because all of this business here with the rocks dragging is sort of intimately related to the rock's rotation, isn't it? Because as the rock sort of tries to rotate, or the planet tries to rotate a bit more, that's sort of going to affect what direction the warping is going to be in. And so what happens here is this lost energy due to frictional heating just comes out of the rotational energy here. This energy here is, in other words, is going to get lower and lower as the planet orbits. So what we think happened to the moon then for this odd process of tidal locking to happen, it's not an odd process, but it's certainly an odd reasoning I'm taking you through here, is that, let's see, let me get some nice gray color for the moon here. Here's the moon like this here. Maybe when the moon was formed, and we'll talk about how that happened, it might have been just spinning like crazy, just really fast spinning. And as it went around like this, it was just spinning like crazy. But of course, as we know, that as the moon goes around in its orbit, it's always getting this warping effect on it. So I'll try to illustrate that now in a more macroscopic way. So let's just say it gets up to here. I want to choose a little gray for that. Gray from it gets up to here, And every so often, as it goes like this, it's sort of a continuous process, but I won't think of it that way. It's going to warp here. Then it's going to warp here. And every position of this moon around the sun, it's going to warp here, then it's going to warp here, then it's going to, it just keeps warping as it goes. When it was initially formed, just warp and warp and warp and warp as it goes around. But then what we discussed then is that this warping represents a loss of energy. So all of these planets here, as they warp, this energy is just going to be leaving the planet because of the rocks going past each other as gravity continues to warp the planet. And what happens is, of course, as I told you, that energy loss is wrapped into this kinetic energy of rotation. If this energy gets lower and lower and lower, that's going to mean that the planet or moon will start to spin slower and slower because it's losing energy due to those rocks going and it'll keep spinning slower and slower until T orbit becomes equal to T rotation. And that's the theory. So let me wrap it up for you one more time here, because I think I've done it. I don't know how good of a job I did, but I think at least I got the discussion out here. So what tidal locking is, in a final summary, it is rotational energy loss due to rock dragging And this happens until some comfort is reached. Until some comfort is reached. And at the moment, the comfort is reached at T orbit is equal to T rotation. Tidal locking. Rotational energy loss due to rock dragging until some comfort is reached at T orbit is equal to T rotation. And the rock dragging line can even be tweaked up just a tad bit here. Rock dragging or warping, which is the consequence of that until this is finally reached. And that in a nutshell is what happened. When the planet or moon finally gets comfortable, that rock dragging, that energy release stops, and the rotational speed of the planet or moon no longer decreases anymore. And I'd also like to say that we have this energy loss. I won't go through it, but there's a similar argument can be had for an energy gain, say if a planet was rotating too slowly. And the reason why it's called tidal locking is because the idea comes from tides. Yes, like the water, the way I discussed, the warping of the water, and the locking here is what eventually leads to this sort of locked condition that the orbital time is equal to the rotation time. So I'm done then with my discussion on how tidal locking works. I hope you got something out of it. It felt kind of messy to me, as it always does. But now I have 2 or 3 very nice professional videos that you can watch now that'll hopefully sort of wrap all this up, and they have nice animations and nice graphics so you can get that idea in your head. But please leave this discussion knowing that it is no coincidence that we always see the same side of the moon. We are seeing the effects of tidal locking that have been going on the moon for billions and billions of years that have made the orbital time of the moon equal to the rotation time of the moon, and that's why we always see the same face. So enjoy the next couple videos, because I did not make them, so that means they're going to be good. Ha ha ha.